I like to solve a good puzzle. It's like, how does the current actually flow? I really want to solve that puzzle. So I'm Katja Nowack. I'm an associate professor in the physics department at Cornell University. And my very broad field is experimental condensed matter physics. We're using experimental physics techniques to explore emergent phenomena and interesting phenomena that happen in all kinds of novel materials. The technique that we use is called scanning SQUID microscopy. SQUID stands for superconducting quantum interference device. What a scanning SQUID microscopy does essentially is magnetic imaging. So for example, one result that we had recently is there's specific topological material, topological state of matter, which is called a quantum anomalous Hall insulator. And if you look at the literature of the quantum anomalous Hall effect, it will always say the current is going to flow along the edges or through chiral edge modes in this material. And we set out to actually just exactly image that. We thought it would be a cute experiment, like we'll see the current flow along the edges, it's going to be great. We'll just confirm what everybody has been saying. And then we started imaging these devices and actually found that the current is not flowing along the edges, but in the interior. Most of the phenomena I've been talking about are associated with the electronic degrees of freedom. So what are the electrons doing in my material or in my device? And I really need to cool down the electrons, kind of quiet them down for quantum phenomena to become important. It's kind of like if they're going on, being too excited by temperature, then those more subtle quantum effects are just not dominant or not present. My lab does typically work all the way, like in between 4 Kelvin and all the way down to 10 millikelvin. So all our cryostats are actually cryogen-free. When I was a graduate student and postdoc, actually, I had to come in, I think every 40 hours throughout graduate school and do a helium transfer. Very tedious. My students are completely free of this because, it's like you close up the system, you push a button, and essentially cools down by itself and needs almost no maintenance or, there's nothing that you really have to do on the cryostat itself to keep it cold, which is great. Sometimes the images that we have to take, if we look at something that gives us very weak signals, it's great if we can take an image for like maybe even 48 hours. I think that's a really big benefit of these cryogen-free systems for us. I think just generally, I think that the future for magnetic imaging is very bright. In probe development right now, we try to make these nanoscale SQUID sensors, and one aspect I am actually pretty excited about is that we're trying to do this on the wafer scale. So our vision is to make these SQUIDs kind of batch fabricated, and one aspect that I hope will work out is that we then can also go out and share these sensors with other people in the community. And so if we can make these SQUIDs on a wafer scale, then maybe we can go out and share them with more people, and then more people will start doing magnetic imaging. That would be wonderful. In the field of quantum materials, I think there's a lot of room for studying phenomena on the local scale. There's a lot of different local probes that you can use. I think magnetic imaging is really versatile at looking at these phenomena in many different ways, and so I'm really looking forward to keep applying it to quantum materials, and I'm also really looking forward to maybe pushing the frontier of the magnetic imaging and the probes that we use further as we go.